Huh? Oh, God. Okay, Brooke, can you hear me?
Yep.
Okay, if I step over here, can you still hear me?
Yes.
Good. Okay, so this is working. All right.
Yeah, I have a, I either have chapel or my crossbow golf class during that time, and then I have to.
Okay, Brooke, I'm going to need you to talk to me again. Do the slides move for you?
It's on the epithelial tissue.
They're not moving?
No.
They're not moving. Okay. Let's try this again.
I can pull up the PowerPoint on my.
Let me try this again, see if this will help. All right, let's try this again. All right, so can you see that? And now does it move?
No.
No?
No.
Can you see the slides?
I can see a slide. Yes.
You see a slide and it doesn't move.
No.
Yeah, like on the Zoom, I can't get I can get it to move here, but when she looks at it. Okay, stop share.
You're sharing your
And
screen.
then, okay, come on. Okay,
Now go back to Zoom. And then
share.
Yep, share your screen and hit that. Yep. And then hit share. And then maybe now she can see you move it.
Okay, can you see that, Brooke?
Did you move it?
No, we didn't move it from epithelial tissue.
We didn't move it.
Okay.
First of all, do the slides move now?
Yes.
They move now. Okay. So if I do this, okay, now can you see it?
Yes.
And does it move?
No.
No. I think I may just do this and then just do this since that works.
Okay.
Because when I try to do screen show, it doesn't
Okay.
work. So. All right. Let's go ahead and begin. We're going to talk about epithelial tissue. Let's start with a word of prayer. with a word of prayer. Gentlemen, thank you. Father, thank you for this cold day. We pray for all of us in this class that we would live wisely, and please help us to stay clear of colds and, of course, COVID-19 and what have you. We pray for our dear sister Brooke as she has to deal with this quarantining and all this business. Please help her to feel well and stay well, and for us too. Now, Lord, as we embark upon this foray into histology, give us ears to hear and minds that want to comprehend. In Jesus' name, amen. All right, epithelial tissue covers things. It covers things. It will cover surfaces. Epithelial tissue can be absorptive, it can be protective, it can be secretory, it can be a lot of things. An epithelial tissue that essentially provides a boundary or border, it's typically called an epithelial membrane. They can be single cell thick, they can be many cell layers thick. So if the cells are flat like a pancake, then they look like scales on a snake. And in Greek, squama means scale. And so squamous is scale-like, flat. Think of house of pancakes. Nice flat cells. Now, these nice flat cells tend to be resistant to shear forces. So you will usually see these cells at places where the body is subjected to high shear forces. Put thinking caps on and think of some places where you might have areas that undergo high shear force. Anybody care to venture a guess? Joints is skin around joints, yeah. Synovial membranes. Areas of them, yeah, are squamous. Other areas are more columnar. Skin, that has to stretch. Your hand is against your face and it's stretching your skin. And that is an area, this area, because you talk and you chew, it undergoes a lot of stretching. That's shear forces. Also, how about the area in the back of your throat where you swallow? Does that undergo shear forces? What do you think the epithelial layer there looks like? It's squamous. It's squamous. The esophagus, in fact, for that first part is squamous and then transitions into a more cuboidal and then columnar type of epithelium. Other places too, we can think of places, ladies, your birth canal, that's going to undergo big time stretching when you give birth to your children. That area is squamous. The cervix. So the cervix is nicely columnar, and then where it transitions to areas that are high shear forces, it then transitions into a more squamous layer of cells, and it gets multi-layered. And when you have a pap smear, this area is called the transitional zone. That's the zone, and this is called the endocervix. This is called the ectocervix. This is an area that divides. So because material essentially is coming this way, it's passing through here. That's an area that's going to be subject to shear forces through hydrostatic forces. When you have a pap smear, this is the area essentially that gets sampled, because that's the area where we have the most cell division. And that's the area that's most likely to have issues with genital warts and things like that and what have you. So sometimes you can get transitions from one type of epithelial tissue to another, depending upon the needs essentially of that tissue. Here is a stratified squamous epithelium. It's stratified because there are many strata. Strata in Latin means layers. So it's stratified squamous epithelium. This is an example of skin. It's an example of skin. So the epidermal layer consists of keratinocytes. Those keratinocytes at the base don't look very squamous, but as they become mature keratinocytes, they become bags of keratin, and they get flat, and you get many, many layers of those. The main component of dust is dead human skin. You don't believe me? Gather up dust and burn it. It'll smell like burning skin. You're welcome. Hey, we aim to please. So skin undergoes shear forces. It is a squamous epithelium. Squamous epithelia can be simple, that is one layer, or they can be stratified like you see in skin. Now, if the cells are taller than they are wide, then they are like columns. So they're columnar. Columnar. You see columnar epithelia in a big way in the gastrointestinal tract. This is lined with a simple columnar epithelium. A simple columnar epithelium is what you see in the gallbladder, for example. If you do a section of the gallbladder, you see lots of these little, you know, I'm a terrible artist, but most of you already know that. You see this sort of thing like that, and this is a simple columnar epithelium in the gallbladder. You also see that, of course, in the small and large intestine. These cells are absorptive. You may also see columnar epithelia in glandular tissue, where they secrete hormones and other things like that. Here's an example of columnar epithelia, and I will. Is that better? You can see these are nicely stained with a H&E stain here, and you can see the nuclei, and you can see how those cells are nice and drawn out like columns. Those are columnar epithelia. Now, the other thing about these epithelial cells, are these cells just kind of slapped on there, just kind of haphazard like that? No, these cells have junctions that link them together. They have what are called junctional complexes. So if we take, for example, one epithelial cell and then another epithelial cell, these cells are going to sit on something called a basement membrane. This is a substratum upon which these cells will sit. There's a basement membrane. In fact, you can see the color difference here. Basement membrane is all right there. Some of the old books will call this lamina propria. Is that a term any of you have heard before? That's an older term, but it still is used in lots of anatomy, histology books. This basement membrane consists of extracellular matrix molecules. This is a substratum upon which these cells sit. This Material is very important for the life of the cell. So if you have a nucleus here at the apical surface, so this is apical here, this is basal, this is so-called basolateral, and this is so-called ipsilateral. Ipsilateral, like that. You have at the near the apical surface junctions. This is called an adherens junction. This is called, well, excuse me. And then above the adherens junction, you have something here. I should have done that in a different color. It's a different thing. This is called a tight junction. These proteins in these junctions, if you don't have those proteins, guess what happens to these cells? They fall apart and they start to grow uncontrollably. They become tumorous. So this junction not just holds the cells together, it also controls their growth. Because if one cell gets damaged, now this cell says, oh, I should divide and fill in the gap. Without that junction there, it doesn't have proper junctions, it just says grow, 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 grow. That's what it does. If you get to the magical age, it used to be 50, now they've lowered it to 45, and you have that thing called a colonoscopy. If you have a polyp, one of the things the pathologist is looking for is, do you have junctions? If you don't have junctions, that means that adenoma is a lot more advanced. If it has junctions, you're probably safe. This is a case with all epithelial cell layers. They are linked together by junctions. So you can't just have any old thing flying in between these cells. These cells are very tightly pressed together in a very deliberate way. So if you want to get absorbed into the bloodstream here, this cell's got to take you up, and that cell will recognize you specifically and do that. It won't just say, la, 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 let's go into the cell. Nope. Very specific mechanisms by getting in, and it can't say, I'm going to do sneak attack in between the cell. The cell essentially has to have specific mechanisms. There are a few things that are taken up this way, like magnesium, for example, is taken up through junctions. But most everything else, got to go through the cell. Evan?
So when you're saying like the colonoscopy thing, if they see no junction, does that lead to colon cancer?
Yeah, that's one of the stages to colon cancer.
So
Colon cancer is a staged thing. Yeah.
So if there's no junction, are you guaranteed to have it? Or
You're at a much higher risk for having colorectal carcinoma. Yeah. Now, if the cells are as high as they are wide, and they're shaped like a box, they're shaped like a cube, so they are cuboidal. Cuboidal. Cuboidal epithelia are seen wherever epithelia form a tube. So if you think of tissues that have lots of tubes, things like livers, things like kidneys, things like prostates, things like seminal vesicles, things like sweat glands, things like the pancreas, things like thyroids, you're going to have columnar epithelia. So they're found in the ductal systems of endocrine glands, ductal systems of the kidney, so on and so forth. And you can see they form tubes. These are also linked together very tightly with junctions so that the tube doesn't spring a leak. And here is a picture. This is from a liver. And tell me what you see. Cuboidal epithelia. Yes, Ms. Katja? That's a multi-step process as well. Yeah, and one of the first things that happens, well, they're derived from melanocytes. Melanocytes don't have super tight junctions to the cells around them in the first place, but there's several steps on the way to becoming melanomas, and that pathway is pretty well worked out. That's why you're starting to see targeted therapies against melanomas that are proving to be pretty effective. Used to be melanoma was bend over, grab your ankles, and kiss your fanny goodbye. Not so much anymore. People are surviving much longer with melanoma. The big issue with melanoma is catch it early. Catch it early. And the melanoma migrates down deeper into the skin. And that's why in a biopsy, that's one of the things you're looking for is the down migration of the melanoma. It's looking for lymph or blood so it can spread, and it can go pretty near anywhere. Punch biopsies, yeah. Punch biopsies are the standard way essentially to search for melanoma. The scary part is if you don't see it, it might have all left. So not seeing it, it being clear, might mean you got it all, but it also might mean that it left. So it's someplace else in your body. That's the scary part about melanoma. To reiterate, single-celled epithelia are simple. Multi-layered epithelia are stratified. And here's just another nice example. This is a picture shamelessly stolen from your book without apology of your skin. It's a very nice example of what kind of epithelium? Stratified squamous epithelium. Tuesday and Thursday, you'll see lots of examples of these. We have lots of examples of skin and what have you. Now, while I have you guys here, let me point out, we have a blood vessel here. Blood vessels, particularly capillaries, have a layer of cells that are squamous cells, but those squamous cells form a tube. So capillaries are one of the unusual cases where you have squamous cells forming a tube, not cuboidal cells forming a tube. And these are called endothelial cells. Endothelial cells. And endothelial cells tend to be very tightly knitted to each other, albeit they will also tend to have some pores in between them so that you can get some fluid exchange with the tissue. And look at that, I anticipated what I was saying. So these line blood vessels, even in arteries and veins, the inner intimal layer is a squamous epithelium. And in capillaries, which are just a single cell thick, they're very well designed for the diffusion of fluid into the tissue. And then the diffusion back into the bloodstream as well as the blood courses through the tissue. The single cell thick vessel also is extremely well designed for the diffusion of gases. The gases, therefore, don't have to diffuse very far. You don't have all these layers to go through. It just diffuses right through these layers very easily. And so capillaries are one of the primary places where gas exchange will occur in tissues. Not to say it doesn't occur in larger vessels, it does, but not nearly as effectively as it does in capillaries. Now, there are a group of cytoskeletal elements inside cells called intermediate filaments. And a subgroup of the intermediate filaments are the keratins. Keratins, when they are very highly cross-linked, can be very tough. And if you don't believe me, just take a look at your fingernail and just pound on it for a little bit. That is essentially keratin. That makes your fingernails. The claws of birds, the claws of your cat when your cat digs her claws into you. Excuse me, bad kitty. And those sorts of things, they're the result of keratins. Skin is an epithelium with lots of keratin. The keratin reinforces the toughness of the skin. Some epithelia are keratinized. They have keratins to make them tougher. Others are not. They're non-keratinized. So some linings are non-keratinized membranes, others are keratinized, the skin being the best example of a keratinized epithelium. As we said, the epithelium sits on a basement membrane. This basement membrane consists of these extracellular matrix molecules. That it's a mixture of rather complicated molecules, all very interesting. And this gamish of molecules is just collectively known as extracellular matrix. Glands. There's two types of glands. Endocrine glands secrete their products directly into the bloodstream. So an endocrine hormone, an endocrine signaling molecule, gets into the bloodstream and ends up eliciting biological effects far from the source where it was made. Exocrine glands are derived from epithelial cells. The tube into which they will excrete, that usually leads to a blood vessel, or the blood vessel will go straight through the gland. They will secrete into a capillary bed, and then it's taken up by a capillary bed or something like that. Those secretory cells are usually columnar epithelia, usually. And then you have another group of glands called exocrine glands. Exocrine glands secrete their materials into ducts, into tubes. So sweat glands, great example of exocrine glands. You secrete into a duct, that's your eccrine sweat gland, and so on and so forth. So exocrine secrete into a duct, endocrine glands secrete into the bloodstream. Yeah.
So with endocrine glands, it's talked about with the factors, and so like with blood pressure, is it the endocrine glands that are blood pressure?
Yeah, blood pressure, actually, there's several things that regulate blood pressure, from angiotensin to endothelin to, depends on the organ. Different organs secrete different regulators of blood pressure. So blood pressure is kind of multifactorial. And then there's heart rate as well that affects it, and vasodilation. Oh yeah, it's a constant minute by minute sort of things. And then some things will regulate blood pressure more long term, like the kidney, which regulates blood volume. That will regulate blood pressure long term. Other things are more moment by moment, like baroreceptors, which we'll get to, and things like that. Yeah. Yeah, Dane.
I don't know that topic, but so are stratified and complex?
Yes. Yes. Complex epithelia is sometimes used to refer to epithelia that have multiple cell types. The books are not consistent in the way they use that. Complex is usually reserved for example, the airways. The airways, you have ciliated cells, and then you'll have goblet cells that secrete mucus, and then you'll have C cells that are the stem cell population, and then you'll have this surveillance cell. No one can agree on what to call the bloody thing, So that some people will call it, even though it's a single layer of columnar epithelia or pseudocolumnar epithelia, some would call that a complex epithelium for that reason, even though it's really single layer. All right, so endocrine secrete their stuff straight in the bloodstream. And so examples of various glands and things like that. Ooh, that's a mistake. That should say, no, that's right, exocrine. Yeah. No, I'm right. I'm sorry, I'm all goofed up here. Yeah. Lacrimal glands, your tear glands, those are nice examples of exocrine glands. Sebaceous glands, if you go swimming, sometimes you get out of the water, your hair feels a little bit oily. Bethany, you probably had that happen teaching swimming. Probably get out and your hair just feels yucky. That's your sebaceous glands responding to oil being washed out of your hair, and they just kind of go gut with the oil. And you have those on their skin as well. They secrete this mixture of fatty acids that's collectively known as sebum. It's actually a pretty complex mixture of different fatty acids and things like that. Sweat glands, which secrete, well, liquid, but also salty liquid. And then some things are excreted into the sweat as well. And then glands also that you find throughout the digestive tract. The pancreas is kind of a two-tone thing. It's an exocrine and an endocrine organ. The liver also secretes things into a ductal system. The prostate, the seminal vesicles, they're examples of exocrine glands and so on and so forth. And I include this here just to, again, remind me to emphasize the importance of the extracellular matrix. Cells respond very often to growth factors, and it's clear that growth factors are bound by the extracellular matrix. They can actually be concentrated underneath the cell, and when a cell gets damaged, they can be released, and they can tell other cells to divide and replace it. And it's clear that certain developmental deformities are due to defects in the extracellular matrix. So this is quite important stuff. It was written off as just cellular glue, and now it seems to be more than that. It's very important. Very good. That leads us. Are there any questions about epithelial tissue before we move on to connective tissue? All right. Let's talk now about connective tissue. There's 4 types of connective tissue: cartilage, bone, blood. You might say, what on earth is blood doing there? Well, blood, whenever you section tissue, in between tissue, you see blood. So blood was classified very early as a connective tissue. And because people aren't really sure where to put it, it's staying in connective tissue. So that's kind of historic. Then you have so-called connective tissue proper. That's what you would understand as tendons, ligaments, things like that. So some connective tissue has a lot of water in it, and it's so-called loose connective tissue, sometimes known as areola tissue. So connective tissue has a lot of a protein called collagen. And in loose connective tissue, there's not much collagen, and the collagen is all over the place. It's not lined up in any specific way. It just kind of goes haphazardly this way, that way, and it's not very dense in the tissue. So lots of water, collagen is scattered and haphazardly arranged, and there's not that much of it. You find loose connective tissue in the dermis, which is underneath the epidermis. Here's an example of some loose connective tissue, and you can see kind of the collagen's going every which way but loose, and in preparation, you lose the water, so you see a lot of empty space. That's where the water was, essentially. This type of tissue is a good shock absorber. So if you think about essentially blows to the skin that you might have, or rubbing of the skin, so on and so forth, this is able to disperse forces quite effectively. So if Evan gets in the batter box and the ball gets away from the pitcher, or I don't know, maybe in Evan's case, maybe he was actually aiming for you, and Evan, say, takes one on the shoulder, the ball hits, but the ball essentially, before it's going to really whack on the bone and really bruise the bone, it's got to, that loose connective tissue will disperse a lot of the force. Now, is it going to smart after he gets hit by an 87-mile-an-hour fastball? Yeah, but will it do as much damage as it could have? No, because those forces are being nicely dispersed throughout that loose connective tissue. Or if, after going on base, he goes around the bases and he slides into home, that skin is being stretched as he slides, sticks that foot under and slides. The force now, that rubbing is getting dispersed because of all the water and because the collagen is in lots of different directions. That keeps the skin essentially from going like this and then getting sloughed off, which would not be good. And if he does get injured, if the leg, say there was some gravel, which there should not have been if the field was properly rolled the way it should have been. If he gets a scrape, the scrape is only going to be epidermally deep, and then it will just essentially fill in, and he's fine by the next game, essentially. So my son-in-law, who's a pitcher, keeps telling me, yeah, those directions that the catcher's giving you, beanballs in there somewhere. Keep asking him, which one is it? He said, I'm not going to tell you. He says, it changes with every batter. Dense fibrous connective tissue. Dense fibrous connective tissue has a lot more collagen, but the collagen is not lined up in any parallel fashion. It's still at various angles to each other. So it's a lot denser. This also will be able to resist shear forces in lots of different directions. So that's your dense fibrous connective tissue. Dense irregular connective tissue has the collagen again at perpendicular angles. This is what you'll find on sheaths and capsules that surround organs. So the glisson capsule that surrounds the liver will have dense irregular connective tissue. The Cooper's capsule around the kidney will consist of dense irregular connective tissue, and so on and so forth. The peritoneum and the adventitial tissue that surrounds your body cavity, that's composed of dense irregular connective tissue. And you look at this, there's a lot less water in it, isn't there? What do you notice about the collagen? Yeah, it's kind of going all over the place, but there's a lot more of it. So this will be very good, essentially, at dispersing forces that are being put on it. Then you have dense regular connective tissue. Now, essentially, the collagen looks like a marching band, all standing at attention and going in the same direction. So this is what you'll see at bone and muscle. So bone to bone, muscle to bone, so on and so forth. So your tendons, bone to bone, ligaments, muscle to bone. And they are meant essentially to resist forces in particular directions. This is the reason why when you get eccentric forces on joints, the ligaments tear, because those ligaments are going in one direction. So you soccer players, when do you tend to tear your ACL? This is the part where you answer. Yeah, when do you tend to tear the ACL? It's usually, yeah, it's usually rotational. The foot is fixed and then you rotate. The knee is pretty good at this, not so good at this. It's when the foot is planted, you stick your cleats in the ground usually, well, Evan's not here, so I'll pick on the softball players. Softball too, when you get stuff like that where the cleats go on the ground and then you get this kind of force like that. The knee now, which has these tendons, now they're being forced essentially, the tendons like this, and now you get a force essentially cutting across what it was designed to. That's the times you get those tears. And you can have a type 1, type 2, type 3 tear, depending upon if it's just damaged, type 1, if it's partially torn, type 2, or it's completely torn, type 3. I'm preaching to the choir here for some of you. And some of you may have had even tears like that. So that's why, and that's why Evan's dad is constantly, oh, that's why he went to the bathroom, because he's drinking Monster. Enough caffeine in that to make you run to the loo. I pick on Evan because I really like him. What was I saying? Oh, that's why Mitch is constantly saying, you need to make sure that you balance of forces, because these tendons are meant to work in a certain direction. If you don't work in that certain direction, you start walking funny, you're putting eccentric force on those tendons. That stresses them. That puts micro tears in them. That damages them and what have you. So if you look at these, you can see they're straight. This is meant to resist forces in this direction. If you put force across this like this, that's what causes the damage. But they're very good at resisting forces in that particular direction. Any questions about connective tissue proper before we move on to cartilage, bone, blood, adipose tissue, and stuff like that there? Cartilage. So cartilage is an elastic tissue that is avascular and is smooth. It acts as a smooth surface for bone articulation within joints. It plays a role in bone formation. It also provides structural support. For example, the cartilage rings in the trachea provide nice, flexible structural support. The majority of the tissue in cartilage is extracellular matrix. And then you have these cells called chondrocytes. Chondrocytes. The chondrocytes are responsible for secreting and maintaining the extracellular matrix of the cartilage. So the biggest role of cartilage at joints is as a shock absorber. Bone is meant to be rigid. Not meant to, bone is meant to essentially neither bend nor break. Cartilage is meant to kind of bounce back, roll with the punches a bit, and go with it. So there's three main types of cartilage. Hyaline, that's the majority cartilage, hyaline, elastic, and fibrocartilage. Hyaline, elastic, and fibrocartilage. Hyaline has a glassy appearance. Hyaline in Latin means clear. So it's kind of a glassy appearance. You find it on articular surfaces. And also in places where it'll provide structural support. Elastic cartilage. Elastic cartilage has a dense network of branching elastic fibers that consists of a protein called elastin. Elastin. It is flexible, but it's firm, and it's even more flexible. You find elastic cartilage in your larynx, so your vocal cords attach to elastic cartilage attachment sites. The epiglottis that acts as a trapdoor to keep you from aspirating food when you swallow it. That's made of elastic cartilage. And then the pinna of your ear is nice and flexible. That's made of elastic cartilage as well. Finally, you have fibrocartilage. Fibrocartilage. This has collagen fibers and then it has bands of extracellular matrix. You find this in the meniscus in your knee. those little wedge-shaped discs of cartilage that are not attached to the femur and the tibia, but you've got those little wedgies that are on top of the tibia. Those are made of fibrocartilage. You also find them in the intervertebral discs between the vertebrae. All right, if we look at hyaline cartilage, this is stained with a Alcian red stain, I think. We can see here, we've got this beautiful connective tissue. Now, this particular hyaline cartilage has a so-called perichondrium. Articular cartilage does not have a perichondrium. That's why articular cartilage does not regenerate. When it's gone, it's gone. But stem cell scientists are designing ways to get it back. So there is hope. Yes? There's two types of arthritis. There's rheumatoid arthritis, in which you have an immune response against the synovial tissue. That inflammation, you get formation of so-called pannus, and the knee essentially just becomes immobile. Then there's osteoarthritis, where the cartilage is degraded, and then it starts to degrade the bone. And then you have a bone-on-bone situation, and that's why you get the knee or the hip replaced. Right, can't regenerate. Yeah. Lots of other cartilage can regenerate. Lots of hyaline, for example, the nasal cartilage here is hyaline cartilage, but it has a perichondrium. So does hyaline cartilage in your trachea. That can regenerate too, because it has a perichondrium. Articular cartilage doesn't have a perichondrium. So these chondrocytes, they begin their life as so-called chondroblasts. Chondroblasts, they migrate from the perichondrium, and notice they're in clusters of two or three. They tend to hang together like HES students, and they secrete the extracellular matrix. They get trapped in it. They work themselves out of the job, essentially. They mature into chondrocytes. One of the common elements of the extracellular matrix found in cartilage is type 2 collagen. That's a cartilage-specific collagen. And then they make a specific cartilage proteoglycan. Cartilage-specific proteoglycan. Again, some hyaline cartilage has a perichondrium. It can regenerate. Articular cartilage does not. Elastic cartilage is similar to hyaline cartilage, except that the extracellular matrix contains this defining feature of elastic fibers. Better? See the stringy things going through? That's the elastin. That's going through the elastic fibers. And this is a section essentially taken from somebody's, well, a dog. Actually, this is from a dog's ear. And then I don't have a good picture of fibrocartilage, but fibrocartilage essentially has lots of laminations. Can you see that? Everyone see that? See the layers? That's very, and the cells too kind of line up in chains and they form layers. That's very characteristic of fibrocartilage. And because Brooks on Zoom Let me just show her this on Zoom. See the layers there, Brooke?
Yes.
Yeah, that's very characteristic of fibrocartilage. All right, any questions about cartilage before we get the bone? So bone, long bones are made from cartilage that is converted into bone. Flat bones are made by a ossification process where you get cells called osteoblasts. Osteoblasts that essentially move in, lay down a matrix, the bone forms essentially, and the osteoblasts become embedded in the bone. They then become osteocytes. The osteocytes have cytoplasmic extensions. They communicate with each other. If the bone is damaged, they no longer communicate with each other. That tells them to make new bone. That's how the bone gets repaired. You have another cell that you find within bone called an osteoclast. And the osteoclast, when bone is damaged, the osteoclast comes in and cleans up the broken bits of bone so that the osteoblast can come in and make more bone. And in some postmenopausal women, osteoclast activity exceeds the activity of osteoblast because of low estrogen. Osteoclasts are inhibited by estrogen. So as estrogen levels tank, your osteoclast activity goes up and the bone density goes way down. And that's called postmenopausal osteoporosis. And it tends to run in families. My cousin, his dear wife, Barb, for example, when she was 52, her doctor said, "Hon, you have the bones of an 80-year-old." It runs in her family. Barb is small, she's petite, she's very lightly built, and it runs in her family. So yeah.
When does that generally like affect? How old do you generally get?
It depends. Depends when you undergo menopause, because menopause varies. If you've had cancer and you get cancer treatment or something like that, menopause will occur earlier. Some women don't have a high so-called ovarian reserve, so they may go through menopause earlier as well. Also, the bone density you have at your peak bone density, the higher it is, the lower your risk of osteoporosis. Barb, apparently, when she was younger, my cousin Barb, she didn't eat very well. So her bone density was terrible. So she didn't have much to lose, unfortunately. But she's held her own. She's taken her medication and her diet is stellar and she stays active and she's held her own. So kudos to Barb.
Is there a way that you can build density? Like,
Yeah, there are medications that can do that.
is
Yeah.
she like regaining a normal level or is she just maintaining?
She's maintaining. She's gained a little bit, but she's pretty much maintaining. It's not getting worse. Yeah. 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 Stress-inducing exercise, weightlifting, light amounts of stress on the lower body, things like that. Running is usually not recommended for older people just because of what it does to joints as you get older, unless you're Chuck White. No, Chuck had knee surgery, his cartilage. He was 68. His cartilage was a cartilage of an 18-year-old, according to the doctor. And the guy's been running since he got out of the diapers, and he hasn't stopped. It's like, how? 74? 2? 3, 73. 73. He still runs. Well, he speed walks, but. No, it affects you long term. That's why one of the treatments of it are estrogen mimics, essentially. So these drugs called SERMs. You heard of SERMs? Yeah, birth control though will increase the risk of ovarian cancer. So that's why you use modified drugs that help with the bones, but they don't increase the risk of ovarian cancer. That's why they're estrogen receptor modulators. Selective estrogen receptor modulators, that's what SERMs are, like tamoxifen or viloxifene or drugs like that. Yeah. Guys are pulling me off topic. It's my fault. I shouldn't mention it, but hey, you know me, my big mouth. So bone gets laid down in these concentric circles, and you have this blood vessel that around which the osteocytes will make the bone, and that's called a Haversian canal. And this whole thing here with the Haversian canal is called an osteon, and the dense bone is usually called compact bone. You have other areas of the bone that aren't as dense, that's called cancellous bone. Cancellous bone. And then in the center of the bone, you have the marrow, and there are areas, some bones, where the marrow is very actively making blood cells. Certain bones, like the sternum, is very active. Other flat bones are active. The long bones, a little bit, well, very active earlier in life. Later in life, not quite so active. That's why if you have bone marrow cancer, one of the places they do is they tap the sternum, because that's one of the most active blood-making bones in the body. And notice in this picture too, how the osteocytes, how they're connected by these cytoplasmic connections. That's really important. That's how they communicate. They secrete molecules to each other that says, I'm okay, you're okay, everything's IV, yeah. And then if there's a break, oh, not okay. I'm not okay either. Okay, we need to do something about this. And that's essentially what helps with that. And this is a really nice picture that shows you the Haversian system. Bone is a tissue that does not have a robust blood supply. That's why treating infections in bone or cancers in bone is so hard to do, because getting drugs and things into bone is very hard. You can do what's called an interosseous injection, where you drive a needle straight into the bone, and yes, it hurts. And then you release the drug into the bone medulla in the center of the bone. You don't want to do that too much. It can, yeah, it can. That's why it's only recommended like once or twice. Yeah. Now, teeth are different. Teeth are composed of a material called dentin. Dentin, as it turns out, with this other stuff called enamel. And enamel is a composite of a protein called amylogenin. Amylogenin plus this mixture of hydroxyapatite crystals. This is actually the hardest compound in your body, enamel. Very, 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 very hard. So the dentin composes these tubes where you have these pulp cells, and then the amyloblasts early in life will secrete the enamel essentially that forms the crown of the tooth. And then later on, when the tooth is fully mature, those cells die off, and then the tooth is just recalcified passively through calcium in your saliva and precipitation on top of the tooth matrix and so on and so forth. And here are the dentin tubes. Those dentin tubes are anaerobic. So after you die, those tubes, because they're not exposed to the air, that's one of the best sources of DNA for after you've died. That's why to identify someone's remains, sometimes the teeth will be drilled, and that's where the DNA will come from, because of those dentin tubes. Like bone, dentin can be remodeled according to stress. And that's why using braces essentially can change the molding, the bite essentially, because that tissue remodels according to stress, just like bone does. And so you have your, you have your enamel here on the outside. Then you have the dentin tubes, you see the tubular structure. And then down here you have the pulp. So if you get a little cavity here, you're not going to feel it. Once it gets to the dentin is very susceptible to erosion. If it erodes through the enamel, the erosion through the dental is very fast. When it gets to the pulp, then it really hurts. And then you get the so-called root canal. And this piece here essentially is just removed. And then this is just filled with a filling, and the tooth is dead. But it'll still recalcify passively. And enamels, we said, very highly calcified. It can only be passively regenerated. And if you look at enamel, it's a structure with lots and lots of fiber-like structures. Those are protein, calcium structures that are heavily cross-linked. And artificial fillings today consist of these resins that are hardened with UV light that can actually match the texture and the strength of the enamel, which Greg gets to learn all about when he goes to dental school next year. So proud of you, Greg. Well done, brother. Well done. But this stuff gets called colloquially tooth plastic because you can mold it to look like any tooth. And then it's usually put on softly, and then the dentist will have you bite down so that it molds to your bite. And then they'll say, open up wide, and then with the UV light, and it hardens it. The chemistry in these is just genius, absolute genius. And this is a table stolen from your book. Please take a look at that table and be familiar with the different types of epithelial membranes. And this site is a very cool site. If you want to review different types of histology, this is a, oh, you're kidding, you moved it. Oh, this summer it was just fine and they just moved it. Okay, I will fix that and change that, but anyway. Okay, let's talk very briefly about organ systems. So organs, tissues are made of cells. Cells form tissues, tissues then form organs, and then organs form organ systems. These organ systems consist of organs that are dedicated to common functions. Now, classically, there's 10 of them, but with the immune system, that makes 11. So well, yes, I already said this. So organs are composed of tissues, organ systems are composed of organs. And here are the 10 that we will look at in this class. So the integumentary system, that is a system of skin that covers your body. The nervous system, brain, spinal cord, regulation of systems and consciousness and things like that. Endocrine system is highly regulatory. The skeleton provides the scaffolding upon which things attach. The muscular system helps the scaffolding move. Circulatory system is to move things around the body. It's the information superhighway of the body, if you will. Immune system keeps you from getting sick. Respiratory system for gas exchange. Urinary system, very important for regulation of ionic composition of the blood and volume of the blood, and then excretion as well. Digestive system to bring energy into your body in the form of food, and then the reproductive system to perpetuate the species, and also for bonding of husband and wife and so on and so forth. Okay, that is all with this. We will start on chapter 2. We'll give you a whirlwind review of cells and how cells do business. And then we'll look at how cells regulate their environment and then how they can tweak that to actually make action potentials. Stay warm in Uncle Jim there, Evan. Oh, lovely. Cool. Okay, Sarah, thank you. Thank you. Okay. Oh, okay, you're gonna miss that. So, when you guys are on the bus, does it help to do Zoom or no?
It depends if we can get a signal or not.
The buses are supposed to be wired. Now, that's one of the ways they sold it to us, was that the buses are wired. That students are going to be able to communicate via class because the buses were wired. And now it seems to me that was balderdash.
Yeah, it's probably just